Hello and welcome. You are looking at Algebra Review. Now, all this review material is to help prepare you for what you're going to learn in pre-calculus. The topics covered you can see below. Now, each one of these I have a title for in some videos. If you see the last 5 videos that I made, they have these titles, so you can go to them for more explanation of things, like without just doing example problems. What I'm pretty much going to do is a bunch of example problems. I am going to have this big frame up at the top with information on every slide that has to do with the problems that I'm covering, but I'm not really going to be talking about them a lot. I'm mostly just going to explain how the problem's done as opposed to, other things that explain these things a little bit better. So if you want to look a little more in depth, please take a look at those individual videos. Okay, let's go ahead and get started. So I'm going to do these 3 example problems right here. Plotting points, so all this stuff, as you can tell, just as I was talking about up here, this stuff up here has to do with what's down here. Midpoints, distance, everything like that. So this first example question says, plot the points and find the distance between the points. So I have the points -3, 8, and 1, 5. Now, if you don't have a graph, you can always feel free to draw yourself a graph, and it doesn't have to be a very, very perfect one. All you have to do is make sure that you identify what points it is that you plotted, because these values actually matter. What we need to do is find out how far to go, how far it is between here and here. How far we have to go. And this distance d here is not quantifiable in a counting sense. I can't just say 1, 2, 3, anything like that. I can't count diagonally. However, I can count vertically and horizontally. So what I can do in its place is make a right triangle. And the right triangle is made because I have a vertical line and a horizontal line, which are perpendicular to one another. So there's a right angle. This is a right triangle, and it has 2 separate lengths. It has this length here that's the difference between my 2 y values. If I have some y value like 8, I'm subtracting the other value 5, and I get the distance 3, or I can count 1, 2, 3. Same with going from -3 to 1. That takes 1, 2, 3, 4 steps to get there. And voila, I have a right triangle with leg lengths 3 and 4. So from here, I can almost ignore a graph and almost even ignore what's being asked here. All I need to find is now this, essentially the hypotenuse in a right triangle. So I can use Pythagorean theorem right here, a squared plus b squared equals c squared, because I have 2 of the numbers. And I can solve for d. So d is 16 plus 9, or d squared, excuse me, which is 25. So d is the square root of 25, which is 5. Now, a couple things to note. If d squared is 25, ideally d is really plus or minus the square root of 25, which is plus or minus 5. However, we are referring to distance, not just value, and distance is always positive. So essentially, we are taking the absolute value of our number regardless. Just like this 3 here, right? If I was going from 8 to 5, technically that number would be -3. But I'm not too concerned about that. And even if I was, I would square the number anyway, so it would still become positive. So that's neither here nor there, to be honest. Another way I could do it is using just the distance formula straight up, but ideally that's what I did. I took the difference in my 2 x values and got 4, right there. I took the difference in my y values and I got 3, right there. And d, or in d's right here, the square root of that squared plus that squared. You can see that I didn't do the square root part yet. I could have right here. But it's the same thing, doing nothing different there. However, if you don't have a graph at all, maybe you go straight into this. But remember, it's the difference in distance between your x's and the difference in distance between your y's. Square the 2 values individually, add them together, take the square root. It's Pythagorean theorem. Okay, second problem, plot the points and, well, actually, here, okay. In the first one, they asked you to plot the points anyway, so it's probably good that I did do that. The second one, plot the points and verify that the points form the polygon. Okay, so let's go ahead and plot these points here. Now, it's saying, is this thing going to be a right triangle based on what we plot? 2, 3, 13, 11. Oh boy, that's kind of off the map here. Actually can't reach there. Let's pretend like it was up here. If you can see that. and 522. Boy, let's change the scale. How about that? Let's do every one of these is 2. So 2, 4, 6, 8, 10, 20. This still probably won't perfectly reach, but at least I can get close enough. 10, 20, etc. Okay, here we go. 2, 3. Here's 2. 3 is right there, halfway between 2 and 4. 13, 11, 12, 13, 10, 11, right there. Yeah, this will work out fine. And 5, 22 is 2 more up from 20, so probably about right there. Okay, so what I'm going to make here now, what I'm going to do is connect the points. And they're asking whether or not this is a right triangle. Now, from the first look, you might say, I'm not sure. But then you tilt your head and you go, you know what, kind of does look like a right triangle. And I agree, that kind of does look like it in the sense that this would probably be the right angle. Now, do I know for sure? Well, there are ways to test it. One way is doing something with slopes. Now, I'm not going to talk about that process just yet, or maybe not at all, because there's no problem here with slopes, or because they're talking about distance here. So the other thing I can do is this. The Pythagorean theorem says that in a right triangle, the relationship of your legs to your hypotenuse is this, a squared plus b squared equals c squared, where a and b are your legs, and they're the shorter sides. C is your hypotenuse, which is the longest side. Well, what you can also do is, it's called the converse of the Pythagorean theorem, which says if in a triangle, your two shorter sides, when squared and added together, equals the square of your third side, your longest side, then it is a right triangle. So our question here is, can we find these three distances? And I'm going to go ahead and call them A, B, and C. A, B, and C. Assuming that I understand this is the longest side, and you can calculate them and figure them out, which is exactly what we're going to do. But can I take these three things and set it up with the Pythagorean theorem? Because this only exists in right triangles. See, if this was an obtuse triangle or an acute triangle, then we wouldn't have this relationship a squared plus b squared equals c squared. In an acute triangle, a squared plus b squared is greater than c squared. And in an obtuse triangle, a squared plus b squared is less than c squared. It's only equal in a right triangle. So let's find these lengths, square them, do the proper math, and see if they actually compare equally. So here we go. A, to figure this out, I have to find out this length right here. I have to go from, the right triangle stuff. You can do distance formula as you need to. I really should label these sides, though. So up here is 513. Down here is 522. Down here is 1311. And over here is 23. Okay, so A, I'm going in the x direction from 5 to 13. That length is 8. Again, I'm doing the counting principle significantly more than I do the other one. Going down from 22 to 11, that length is 11. So in this right triangle, this specific one that I just built right here, I can find out A's length by doing 8 squared plus 11 squared equals A squared. So A squared is 64 plus 121, which is, what, 185. So A, for now, I'm just going to put as the square root of 185. Honestly, I don't need to know A's length. I just need to know A squared's length because I'm going to put this in Pythagorean theorem here. But A is this length. It's not a perfect square, and I'm definitely not going to round. I'm just going to go ahead and leave it as that. I could probably simplify the radical. Actually, probably not. But either way, I'm just going to leave that as is for now. Okay, B. B has a right triangle that looks like this one right here. Goes down. It goes over. Okay. Now B's lengths, we are going from, in the x direction, we're going from 2 to 13. That length is 11. And we go up from 3 to 11. That length is 8. Ooh, take a look at that, 11 and 8. So instead of doing more calculation here, take a look. These two triangles are congruent, meaning they share the same, using the side angle side property, knowing that this was a right angle, the one that we built. We kind of gave ourselves that. Side with side, angle with angle, side with side. Two triangles are equal, so I know that by CP/CTC, this is all geometry talk, by the way, this B value is the same as your A value right here. So B is also the square root of 185. Or better yet, B squared is 185. Okay? Now we can determine, well, not now we can determine C. Now we are going to determine C through Pythagorean theorem one more time. And then we are going to set up our Pythagorean theorem and see if everything equated the way we wanted it to. So C goes over this much and down this much. Sorry, it's in kind of bright yellow. But the two lengths here, we're going from 5 to 2. That length is 3, and I'm talking about the x direction. Going from 5 to 4, 3, 2. Now we're going down from 22 all the way to 3. That's 19. Let's set this up with Pythagorean theorem. Let's figure out where we're at with C here. 3 squared plus 19 squared equals C squared. So C squared is 9 plus, I don't know 19 squared. Isn't that a bother? I have my calculator, but I'm a little, whatever. There are other ways for me to do it, but I'd have to talk out loud with it, and I'm not going to be doing that. I just did something wrong. This is 17, not 72. 17, 171 plus 1. Okay, 361. So 361 right here, so C squared is 370. And therefore, C is the square root of 370. But I'm only curious about what C squared, B squared, and A squared are. So here we go. A squared is 185. B squared is 185. We have to determine how this compares to the number 370. Well, thankfully, 185 plus 185 is 370. So how do they compare? They are equal. If they're equal, then this A squared plus B squared equals C squared statement is true. Therefore, this is a right triangle. Now, there was another way to figure this out, something that's actually a little bit easier involving slopes. But for the sake of this kind of problem, we can also prove it using distances only. And we just did right there. Okay, the third problem. Plot the points and find the midpoint of the line segment joining the following points. We have negative 12, 5 and negative 4, 7. So negative 12, 5 and negative 4, 7. I can actually even leave this old diagram right here. I think this is not going to interfere with it at all. Negative 4, 7 is up here. Negative 12 is outward a little bit. 11, 12, and 1, 2, 3, 4, 5. Probably bad that I used the color red. Let's change that. Let's use purple. Okay, we got to find the midpoint of these 2 points. Now, I could conceivably just bring this across and figure out where the midpoint kind of is, just kind of by looking at, seeing it, right? You can probably take a good look and get a good feel, but your thing might not be drawn to scale, or maybe you don't actually plot the points, right? But I have a sense that it's probably this point right here. There are ways to go about this. One is the midpoint formula. And what the midpoint formula says is you are going to average your 2 x values. If you add 2 numbers and divide by 2, you found their average. And you also average the 2 y values. And your resulting solution is a coordinate pair in x value comma y value. So as you can see, to find the x values here, you don't use the y values at all. They have nothing to do with what it is that we're talking about. So they work independently of one another. And same with the y values when you do that. So as I write down these points here, negative 12, 5 and negative 4, 7, essentially what I can say is, and I know it's around here. I might know exactly where it is, but what is the average of the 2 x values, negative 12 and negative 4? Okay, because that answer is also the midpoint. Well, negative 12 plus negative 4 is negative 16. Negative 16 divided by 2 is negative 8. And that kind of makes sense to us, the halfway distance between negative 4 and negative 12. It's the opposite of half the distance between 4 and 12, and we know that number's 8, so this must be negative 8. How about between 5 and 7? You score 5 on a quiz, you score 7 on a quiz. Your average so far is 5 plus 7, which is 12, divided by 2, which is 6. So that 0.86, let's see, negative 86, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Yeah, it looks like it's right there, and that's perfect, so we found it. So that was using the distance formula. I didn't really write the calculations out. My apologies for that. But yeah, you take your 2 numbers and divide it by 2. You really find the midpoint of just 2 values here, not really 3. Now you also know that the midpoint is on your line here, or your segment, which is also another important thing that I can make mention of right now. The next thing I do want to say, and another way I can do this, is by figuring out kind of how far I had to go this way, how far I had to go this way. Because if I cut half this distance, and if I cut half this distance, then I can do half and half, and that will then give me half this distance. Now, what will not help for this problem is finding out this distance and cutting it in half, because we can't count how far halfway is. We'd have to do some other things, such as what I was talking about, going vertically and horizontally. So if I went horizontally, half the distance. Now, the full distance from -12 to -4 is 8. So if I go half that distance, which is 4, right here in green, 1, 2, 3, 4, okay? And then if I go up half the distance between, half the distance of 2, which is just 1, I also find my midpoint. Now, it's not just finding it, but it's actually calculating it. So what am I really doing? I'm going from the number, maybe from the number -12, and I'm adding half the distance to my next point. And I'm also taking the number 5, and I'm adding half the distance to that point. And I'm adding because I'm going over to the right and I'm going up. If I was coming from here, then I'd be going from 7, and I'd be going down. Oh, sorry, that's the y value. I'd be going from -4, and I'd be going to the left 4. And I'd be going from 7, and I'd be going down 1. Okay, now both of these values end up being the same thing, -8, 6. So you still arrive at your final solution there, no matter which way you go about it, either the midpoint formula or getting half your vertical and horizontal distance from either point, and you'll arrive there at that midpoint, -8, 6. Okay, now we're going to talk about circles here. Here's the general equation in standard form. H is the center. HK is the center, where H is the x value, K is the y value, and R is your radius. So this first one, we need to find the standard form of the equation of the specified circle. We have the endpoints of the diameter here of -4, 6, and 10, -2. I'm going to use the graph to help out my explanation with what it is that I'm actually doing. Here's one point, and the other point's at 10, -2, way over. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A little cut off, but 10, -2 right there. Okay, kind of far apart. Now this is a diameter, okay, and these points are on the circle. So 2 things about this. 1, this goes from end to end. 2, half of this distance is radius, which is one way we can find the radius if we know this distance. And 3, we know that the center is somewhere on this segment. Better yet, it's the midpoint of the segment. Now, this is not one where I'm going to say, oh, look, I think it's about there. No, I'm just going to go ahead and kind of figure out what it is. But what I do want to do is make a circle kind of that's close to what it's supposed to be. Like, let's say it's about right there. Just to show you the idea of, okay, this is the circle. So what we're trying to find out is where the center point is, okay, and what the radius is. Now, that's a radius, and so is this as well. If we can find H, K, and R, then we can write the equation, and that's really all we need. So, going back, because maybe you don't have that circle and that stuff in handy, and really you don't need it anymore, it's just the visual to understand what it is you're doing. I have to find the distance here between these 2 points. So, let's go ahead and go down as far down as -2, and over as far over as 10 from the previous point, -4, 6. This is some more distance stuff, just as we were doing before. And what's actually good about me doing it this way, instead of just saying, hey, use distance formula, hey, use midpoint formula, is remember we did midpoint using these lengths as well. We cut them in half. So if I go from the number 6, this is -4, 6. If I go from the number 6 all the way down to -2, I have gone 8 units down. If I go from -4 to 10, I've gone 14 units over. So to find the diameter D, I can use Pythagorean theorem. What I could also do is really, I'm just going to use the diameter to find the radius, right? The radius is the diameter over 2. I could just cut the length in half right now for both of these and just figure out the radius immediately, because that's also what I'm going to do to figure out my midpoint. So instead of 8 and 14, let's talk about going down halfway. What's half of 8? Well, it's 4. And what's half of 14? Well, it's 7. That will lead me to not only my midpoint, but these will also get me to my radius that much quicker, because the radius is this length right there. So you can either find that distance and divide it by 2, you'll get radius, or do this way, and you will find the radius immediately. 16 plus 49, and plus you have smaller numbers. R squared is 65, so R is the square root of 65. Once again, probably not a, probably can't be simplified. That's probably it. Now, again, I didn't, not again, but I didn't truly need to know my radius here. I just did need to know R squared. If they ask you for the radius, okay, that's one thing. But they're asking you just to write this in standard form. And when you write R squared, you will be writing 65. Now, the other point that we need is the HK, the center. The center, once again, is the midpoint of this diameter right here. And we find the midpoint in a couple ways. One way, like I said, is using these lengths here. Full way down is 8, so half of it is 4. Let's go halfway down. The full way over is 14. Half of that is 7. Let's go 7 over. This right here is the midpoint, whatever it is. I don't have it perfectly drawn, but let's go ahead and calculate that. The midpoint is, if we take the number 6 and subtract 4, excuse me, that's for y. We start in 6 and go down 4, or we start at -4 and we go over 7 to the right, then we will land on that midpoint, which is at, let's use a different color. I really got to get better at my color choosing, at 3, 2. So it's at 1, 2, 3, 1. So it's right here. There's your midpoint, which is the center of the circle. So your H is 3, your K is 2, your R squared is 65. So what's the equation? Well, using this, we're going to have X minus H, quantity squared, plus Y minus K, quantity squared, equals R squared. And boom, that's it. So there's your equation. And once again, from the equation, you can pull out information and actually graph the circle as well. Entirely possible to do. Okay, the second problem here. Sketch the graph of the equation by hand. X squared plus y squared equals 10. Okay, for this particular problem here, it's good if you can extract out as much information as possible. This one's going to be a little tricky for a couple things. First of all, where is the minus h? Where's the minus k? Well, if it's missing, then that means you're not subtracting anything, which means your h must be 0, and your k must be 0. Now your radius is the square root of 10, so this is square root of 10 quantity squared. That's why 10 is there. So make no mistake and think that your radius is this number squared or that it's this number itself. It's the square root of 10. So your hk is 0, 0. Your radius is the square root of 10. And we have to be able to use these ideas to go ahead and graph this. The first part's really easy, 0, 0. Here's where we're going to start from. Now, ordinarily, this is what I'd do. I would take the radius, and I would say, I know how to count up, down, left, and right a certain amount, so I'm just going to go ahead and plot those. Let's say the radius was 10. If the radius was 10, from my center, I would go 10 up, plot a point, 10 to the left, plot a point, 10 down, plot a point, 10 to the right, plot a point, and I draw the best circle that I could on paper. Over here, I could use this tool. But, and look how beautiful that kind of is. But this is not a radius of 10. The radius is the square root of 10. So what most people might think is you have an option of taking the square root in your calculator and getting the decimal approximation of 3 point something. I don't know what it is. It's a little more than 3. By all means, feel free. If you want to go up 1, 2, 3 and point something, try and do the best you can. I think that's fair to do. Over there, over there, over there, and over there. But if you're really, really, really well vested in your special right triangles, here's something else you could do. I happen to know that I can construct a sum of 2 square values to give me 10 inside, meaning I know how to get 2 values here to become 10. Now, what I'm trying to do is land on a very specific set of numbers to cross through, as opposed to it's about that. No, I'd rather find something else. I know, this doesn't always come into play. It depends on what kind of problem they give you. And honestly, I'm not sure if this is what they were trying to do. But I know that 1 squared plus 3 squared equals 10, because 1 is 1, or 1 squared is 1 and 3 squared is 9. So if 10 was not 10, but if 10 squared, if 10 is your hypotenuse squared, then the square root of 10 can also be determined by going over 1 and up 3, or over 3 and up 1 in any direction. Okay, because these would be the legs, your A and B in your right triangle. So if I was right here and if I went over 1, I could go up 1, 2, 3. And the distance between this point and this point is the square root of 10, because 1 squared plus 3 squared is the square root of 10 squared. Likewise, I could go over 3 and up 1, and this is another exact point on the circle as well. Over 3, down 1, over 1, down 3, over 1, down 3 here, over 3, down 1 here, etc. These points are exactly the square root of 10 units away. Now that was just through, again, maybe luck of the problem. I'm not saying that, you should be able to know that, but at least for my accuracy, I know that I can land on those points. I know that that will help me out a little bit when I graph. So they kind of hit all those points, ish, right there. Obviously, I didn't do the circle very perfect, but that's one way you can do it. You can get all those points there. You can even get the north, south, east, and west ones. I don't know exactly what number the square root of 10 is. I'm trying to avoid calculator as much as I can, actually. Okay, sketch the graph of the equation by hand. 3x plus 2y plus 6 equals 0. We have 3 different forms that we can graph from here. They all have their own little perks, their own little things. My favorite slope-intercept form, in the sense that I can look at the equation and say I know what the graph will look like without graphing it. But if your y-intercept is a fraction, sometimes I have issue with it. Point-slope form, it's the busiest to look at, has the issue with the minuses, but they're actually pluses, stuff like that, like they're actually positives. But at least, again, if you have a y-intercept fraction here, it's an issue. And this one's okay because if you're already in standard form, and most things are integers kind of like this is really close to standard form, then I have to do the simplest of calculations just to find 2 points. And all you need to do is have 2 points to form a line. So what I'm going to do are 2 different ways. I'll do slope-intercept form, and I'll do standard form. And the reason I'm not doing point-slope form is because I don't know a specific point that is on this graph, at least not yet. And the only other point that I'll know on this graph for sure when I'm doing it is the y-intercept. So slope-intercept form, I'll call it SI form, we have to solve for y. So we have to get y completely by itself, which involves subtracting 3x and subtracting 6. So this will say 2y equals negative 3x minus 6. Divide both sides by 2, and now you're going to get y equals negative 3 halves x minus 3. Your slope is negative 3 halves. Your y-intercept is at the value 0, negative 3. So if I start at 0, negative 3 right here, then I can go down 3 and run 2 to the right, down 3, run to the right, etc. You can do this over and over and over. I can go up 3 and run 2 to the left, like there, and I'm going to get my slope with my y-intercept. And this is what the graph will look like. So let's go ahead and now graph. And not too bad. Let's see, move down a little bit. And that's what your graph looks like. So I put it in slope-intercept form. I know exactly what to do from there, plotting those points. I even know what my slope is, and we're not turned off by fractions when it comes to slope-intercept form for the slope, because we do rise and run and fall and run whatever in a specific way. I'll be talking about slope a little bit more in just a bit. Okay, the other way I'm going to do is standard form. Okay, now in standard form here, it says ax plus by equals c. Now over here it says 3x plus 2y plus 6 equals 0. But if I subtract that 6 over, it's going to look like this. Now I'm in standard form. You're like, what's the difference between these two? Well, one, for whatever reason, the book calls this general form. 2, I'm one step closer to doing what it is that I need to do, which is find more points. Now, I'm going to find the x-intercept and the y-intercept, and they are found very, very easily here. All I have to do for my x-intercept is I have to set y equal to 0. Now, in this equation, if y equals 0, 2 times y is 0, 3x plus 0 is 3x. The only thing that's going to be on this side of the equation is the 3x if I set y equal to 0. The equation says 3x equals 6. Divide by 3, you'll know that x is negative 2. So the x value when y is 0 is negative 2, which means your x-intercept is at the point negative 2, comma 0. Actually, I have to undo this part to make this. Here we go. Negative 2, comma 0. The y-intercept is found by substituting 0 for x, and the same thing's going to happen here. When I substitute 0 for x, this term essentially goes away, and all you're left with is 2y equals negative 6. Therefore, y equals negative 3 when x equals 0. So my y-intercept is 0, negative 3. The last thing I just have to do is plot the 2 points and graph. Now, negative 2, 0, 1, 2, there it is. 0, negative 3, there it is. If you have 2 points, you use your straight edge and you draw your line, and that's it. All you do is first was put it in standard form, and that's why moving that constant over is kind of nice, because all that's left is covering something with your hand and saying, okay, here's what's equal, what do I have to do? Every so often in standard form, your x and y-intercept, just like here, your y-intercept could be a fraction, this could be as well, but the problem with this one being a fraction is now you have to do a lot of rise and run and counting with a fraction at hand. Here, you just got to plot the 2 points and that's it. But this form actually comes in handy pretty well right here. No point slope form apparently for this one. We'll make sure to do some. Okay, looks like both of these will be pretty good for point slope form. Find an equation of the line that passes through the given point and has a specified slope, and find 3 additional points through which the line passes. Okay, let's do part A kind of first here. Ideally, because it's written first, but that's what's going to help us do that. So we have a point, an x1, y1 that exists right here, a slope right here, meaning if we graphed this, we could start at this point and we could do up 1 over 4, up 1 over 4. And actually, it might help to actually have a graph to make this thing happen. But let's first find the equation. This time I'm going to use point slope form, PS form. And the reason is because in point slope form, if you have a point and the slope, then you can just write it in that form immediately. And we have exactly those two things. So y minus y1 equals m, excuse me, not, that's x1. So this was minus a negative 1, I was right, plus 1, equals m times x minus x1. There you go, that's point slope form. You don't have to do any more than that. Ideally, you can just graph right from there. And actually, I might kind of do that because I need to find 3 additional points through which the line passes. What you'd have to do, unless you were really good at looking at slope stuff here, which isn't too hard, and actually I might do that, is you want to just plot more points and graph them. And you can always do just a rough graph. You don't have to be too particular about it, but sometimes we just need the visual, and you just need to say, okay, this is going to help me recognize where I need to go. Over 2, down 1 might be about right there. 2, negative 1. If I use my slope and I go up 1 over 4, when I go up 1, what y value will I be at? When I go over 4, what x value will I be at? So here's going to be another point on this graph, if this helps. From negative 1, we're going to go up 1. The value for y is 0. From 2, we're going to go over 4. The value for x is 6. This is another point through which the line passes. Now, I use slope for that, but I kind of mathematically did that negative 1 plus 1 and 2 plus 4, rise and run. Likewise, you can subtract. We can go down 1 from negative 1 and over 4 from 2. Down, well, I didn't draw the graph really well to begin with, doesn't matter. But down 1 from negative 1 is the number negative 2. Over 4 to the left from 2 is 2 minus 4, so that's negative 2 as well. Negative 2 comma negative 2 is also a point on this graph. Now, how else can we confirm this stuff? We can substitute these values in for y and x and make sure we get that. Take, for instance, 6, 0. I'd have 0. I'd have 0 plus 1 equals 1/4 times 6 minus 2. 0 plus 1 is 1. 6 minus 2 is 4. A quarter of 4 is 1. So that one checks out. Let's try This one right here, negative 2, negative 2. Well, if negative 2 plus 1 equals 1/4 of negative 2 minus 2. So again, substituting negative 2 for x and negative 2 for y. I was about to say negative 3. Negative 1 equals 1/4 of negative 4. So negative 1 equals negative 1. That one also checks out. So they all check out right there. So I wouldn't go trial and error this way. I would do something calculation-wise to figure out what the other points are, just by graphing or just by mathematically doing it. Like if I go up 1 and 4 more, I'd be at the point 10, 1. Because 10 is 4 more from 6, 1 is 1 more from 0. And we could double check that one as well. But those are 3 points right there. I'm going to go ahead and erase some of this work, write down those solutions, and that's it. So we came up with the equation. I didn't put this in slope-intercept form. I didn't put this in standard form. You could have. You would have gotten with a fraction for slope-intercept form. You could have done that, but I just didn't need to. It wasn't necessary for this problem. So the 3 points I'm going to put are negative 2, 6, 0, and 10, 1, in addition to the point 2, negative 1. All these are also solutions to this equation. Okay, the second one here has, and this one I'll just work through more quickly, but I might talk about converting form a little bit. Your slope is 0, and you have negative 2, 6 as a point, your x1, y1. So if we did y minus y1 equals m times x minus x1 minus negative 2 is plus 2, take a look at what happens here. 0 times anything equals 0. So on this side is just 0. Here's y minus 6. I can add the 6 over. I'm going to get y equals 6. Now y equals 6, okay, here's point slope form. Y equals 6 is also kind of y equals 0x plus 6, or plus 6. This is slope-intercept form, but this is also slope-intercept form. This is also standard form, because in standard form, my x term, which I guess 0x plus y, but my standard form, my x is over here, ideally. My y is over on this side, and my constant's on this side. This is your final really good equation you can use. You don't have to really do this. Just use y equals 6. But if you don't know what that means, you can either use this or this to help yourself out. So, how does that help me? Well, if I go back to the graph, if I plot the point 0.6 up here from using this, I can also plot the point negative 2.6 that was there. Everything is going to go on this straight horizontal line. Boom, 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 boom. Let's see. A little smaller, a little greener. Perfect. And it's looking a little bit like that. So you have a flat line right here. Now, you didn't have to graph it, but they ask you to find 3 additional points. Now that you know what the line looks like, maybe that'll help. We found one of them, 0.6. Second point, hey, how about 1.6? Everything you do, y will equal 6, no matter what. Because look, no matter what I plug into x, what happens? It gets multiplied by 0. Whatever I plug in for x, it gets multiplied by 0, so it goes away. My third point, I'm going to put negative 1,974,6. How about that? Huh? It still works. It's not wrong. There's my third point. So you can pick any set of points in this one. This one was more difficult to find the points. This one might be more difficult for you to understand through the graph or whatever it is. You're like, 0, what do I do with that? Is that vertical? No, that one's horizontal. But that is it for that problem, and that sum of point slope form that helps. Okay, here's a little bit more. This time I'm going to talk more about just slope formula. Okay, if you have slope formula, we can do linear equations in slope-intercept form. That's what's required here, so I kept that one up. Let's find the equation of the line that passes through these points. We'll sketch the graph of the equation. Now, I might use point slope form to solve this stuff. That can help me. But what I first need to do for either of those to find any of this is I need to get the slope. Okay, drawing a graph always helps, of course. 2, -1, 4, -1. This is going to look very eerily similar to what we just last did because the line is still flat. It still has a slope of 0 if it's crossing through those 2 points. If you don't believe me, you may use the slope formula. Slope is rise over run, which is change in y over change in x, better known as delta y over delta x, which is y2 minus y1 over x2 minus x1. So if I have an x2, y2, and an x1, y1, I can use exactly that. Your slope is -1 minus -1 over 4 minus 2, which is 0 over 2, which is 0. So the slope is 0. It's a flat line. It'll do one of the things that we did last time, which was equating y just to the same value as any of these points, -1. I know my final equation will be -1. If you are uncertain about that, we can lead into it a couple ways. We could start with point slope form, which means apply your slope, use one of these sets of points, like this one right here, put y minus y1 equals m times x minus x1. Take a look. 0 times this is 0. Y plus 1 equals 0. Therefore, subtract 1, y equals -1. Slope-intercept form, because I'm going to do it with this one as well. I want to make sure that you know what else you can do. Slope-intercept form, you can apply this. Y equals mx plus b. I can substitute an x and a y value into here and solve for what b is. Then I'll rewrite this whole thing with b inside. Now 0x will kind of just get in the way here. Those are going to go away in a bit. This time let's try the points for -1. -1 equals 0 times 4 plus b. 0 times 4 is 0, so b just equals -1. So your slope-intercept form equation is y equals 0x minus 1. But if you don't want to write the 0x, you can just write -1. So you're still getting the same answer regardless. That's the equation. And now we sketch the graph. So I actually sketched it first when I should have sketched it second. This time I will sketch it second. I will only use slope formula, or we'll just talk about it out loud. Okay, second problem here, slope-intercept form. Once again, 1, 6 and 4, 2. We have to find the slope of this thing. Again, rise over run. So what I might do mentally before I do the slope formula, see if you can do this in your head. If I want to go from 2 to 6, I'm also going to have to go from 4 to 1. 2 to 6 is a rise. 4 to 1 is a negative run. From 2 to 6, that value is 4, going up 4. From 4 to 1, that's a run of 3 to the left, so that's a negative number, -4/3. If you don't trust your math with it, go ahead and do, one of these, and you will once again arrive there. So -4/3 is your slope. Okay, so slope-intercept form, we have to get into that form. You don't have to start with it. You may start with point slope form, in which case you can use any of these sets of points. Let's go ahead and try 4, 2 here. So we'll get y minus y1 equals m times x minus x1. Okay. Y minus y1 equals. Now, if I want to do slope-intercept form, what I'm going to have to do is distribute this right here. Then I'll move the -2 over, and then I'll combine like terms. So -4/3 times x plus, it looks like 16 over 3. Okay. Adding the 2 over, I'm going to add that with 16/3. Now, plus 2, it's 2 over 1. If I want to make this a common denominator with 16/3, I'd have to multiply top and bottom by 3. So I can turn 2 over 1 to 6 over 3. And that will still equate in such a way that I can now, like that this number's 2, but now I can add these together. So your final equation in slope-intercept form is y equals -4/3 x plus 22/3. Okay. Now you might ask why I did point slope form here. Well, 1, to have a second option to know what you're doing. 2, like I said, I don't like graphing these when your y-intercept is a fraction. When your slope's a fraction, it's no biggie. We're just going down 4 over 3 anyway. It's not like we're going down 4/3 over 1, which you can do, by the way. But here, I don't want to start from this point and then keep going up and trying to find that fraction again, trying to find it that way. So what I could do is say, okay, point slope form, I know that I can start at the point 4, 2, and then I can apply the slope. So at least there, I know that I'm going through very particular points that I can actually, quantify, because I just know integers because they're on the graph right here. So I can start at 4, 2. 4, 2. Now, granted, you had the point right here anyway. You can also start at the point 1, 6 up here. 5, 6. Anyway, from any of these points, I can go down 4 over 3, down 4 over 3. You can also go up 4 over 3, which you land on the point 1, 6 then, and up 4 over 3. And you can see where it's going across the y-axis. You can see why this y-intercept is kind of not great. Okay, it's crossing at 22/3. That's 7 1/3. Okay, So not a great one, because if I started here, I'd go down 4 right here and over 3, and I'm not a fan of that. So there's one way of graphing. Well, that's the only way I'll be graphing. But another way of solving is going straight into slope-intercept form. Now, remember, we had to deal with fractions anyway here. We're going to have to do the same thing here as well. Y equals m x plus b. If you substitute an xy value, this time I'll do 1, 6 instead. Substitute 6 for y, 1 for x. You are attempting to still get the same b value. Whoops, substitute 1 for x, not x for x, equals negative 4 thirds 1 plus b. So negative 4 thirds times 1 is negative 4 thirds. When I solve for b, I'll be substituting back into this equation up here. Adding 4 thirds to both sides, we end up getting 4 thirds plus 6, right? So 6 is 6 over 1. If I write 6 as a fraction over 3, well, I'm going to multiply top and bottom by 3 over 3, which gives me 18 over 3. And 4 thirds plus 18 thirds is 22 thirds. So b equals 22 thirds. And voila, we go back to the same equation just as we did before. This has negative 4 thirds x plus 22 thirds. So does this one down here. So these are linked with two different approaches. We even use two different points here. And like I said, I'd still graph the same way. But I would probably graph using either the point slope form or these points right here, not from here. Not as fun to graph that way. Okay, a little bit more on slope formula and slope stuff. So just talking about rise and fall here. Feel free to read that as necessary. Use the concept of slope to find t such that the 3 points are collinear. Now, collinear means on the same line. That's all. Any 2 points in a plane are collinear, always. But to have 3 points be collinear, it doesn't come as often. So you have a couple ways of going about this. I can talk about the graph a little bit. Negative 2, 5. 1, 1. And at 0 something. Now what you could try to do is have a perfect graph with it and try and just go through and say, where's that about? Well, take a look. It's a little more than 2. In fact, it's a number that's like, oh man, that's a little too bad. I'm not sure exactly where it is. 0 comma t. No idea what that t is. Darn it. But I do know that the point is somewhere right there. It's 0 comma something. 2 point something. So what can we do then? What can we do? Well, we have some options. First of all, we can find out what the slope of this is. We can put it into an equation, and then we can substitute 0 for x and figure out what y, or t in this case, is. So let's try that one. Let's find out what x1, y1, x2, y2 lead to a slope of. I won't use slope formula exactly. I'll just count right here. We are going to go down 1, 2, 3, 4. This time the value is important to have. We're going to run 3. 1, 2, 3. So your slope again is negative 4 thirds, it looks like. So if I use, let's use point slope form this time. Y minus y1 equals m times x minus x1. I'm using these 2 points right here in point slope form. I don't even need slope-intercept. Well, actually, you know what? Slope-intercept form is also good because you'll find the y-intercept that way. So, sorry. All I'm doing is giving you all the options, okay? I would just do it one of these ways. I wouldn't even think twice about doing it a second way after that. So I can put this into slope-intercept form, and then my b value will be the y-intercept, which is exactly all I need. So I can do y minus 1 equals negative 4 thirds x plus 4 thirds after distribution. Adding this 1 over, 4 thirds plus 1 is 4 thirds plus 3 thirds. So y equals negative 4 thirds x plus 7 thirds. Now that 7 thirds is your y-intercept. The y-intercept is the value of y1x equals 0. Therefore, t equals 7 thirds, which is 2 1/3. 2.3 repeating, whatever that is. And there's the t value. So that's the one that's on the line, or on this segment right here. That's the one that makes these things collinear, that one alone. T at 2 would not have done that. Okay, that's one way of doing that problem. The second way I was just going to say is you put it in a form whichever one you want to just have accepted. In this case, point slope form was perfect. You substitute 0 for x, and then you solve for y. Now, why am I substituting 0 for x? Because I'm doing it at the point when x equals 0. So I'll have y minus 1 equals negative 4/3 times 0 minus 1. 0 minus 1 is negative 1. Negative 1 times negative 4/3 is positive 4/3. You add that 1 over, and you're back to where we just were. Only this time, we're only looking at what is the value of y when x equals 0. And it's there, which is also t in this case. Y and t are the same thing at that place. And slope, once again, you could calculate that way as well if you'd like. Okay, now we're going to start getting into a little bit more special kinds of polynomials and such. We're going to be looking at absolute value, quadratic, cubic, square root, cube root, exponential, logarithmic, and trigonometric. In all of these things, A represents the stretch factor, shift is H and K. Every so often, you're going to have a B base right here, which represents growth rate, but we are not going to be graphing these two. Let's go ahead and sketch the graph of the following equations by hand. Now, by hand, in this case, kind of means no calculator and no table. Can you do it understanding these processes right here? First one, y equals 8 minus the absolute value of x. What I first want to do is write it as close to in this form as possible. Maybe that'll help me say exactly where I want to be. So that also means absolute value comes first. Like that. And it looks like 8 appears to be the k value. Well, what's the h value and what's the a value? That's what I'm curious about. Well, there's a negative in front of here, which this could have been negative 1 times that, it looks like then. Negative 1 times the absolute value of x. If the h is missing, then the h is 0. So here's an equation in this form here. We have kind of enough to state what the vertex of this thing is. Remember, its absolute value as a vertex. It's at the point 0, 8. Okay, so go over 0 and up 8. You're right there. The a value of negative 1 just means, the negative symbol means you're going to flip your vertex upside down. So instead of a V shape like that, it's going to be going that way. The a kind of represents slope. We call it stretch factor only because the slope changes sign when you hit the vertex. But that negative 1 means we go down 1, we go over 1. We go down 1, over 1, etc. We keep doing that. We don't stop. Go as far as we can. Now, when you hit the vertex, you bounce the other way as well. Down 1, over 1, like so. So as opposed to just a linear equation, this one does have a bounce, but the slope is constant. And this is the only one of these with a constant slope. The other ones are specifically called stretch factors in that they will not, I repeat, they will not have a constant slope. So go ahead and graph this here. Make sure you include arrows on your graphs too. There we go. There's your absolute value function for that one. It was best to rewrite it a little bit in that form, see exactly where I was at and what I could do with it. Okay, the second one here. Y equals the square root of x plus 2. Once again, if I wanted to get it in the square root form right here, I want to write as much as I can that looks like this thing. I'm not saying you have to do that, but some people like to make a lot of use out of that. So nothing needs to be rewritten in order, but what I do want to do is put an a value in front of 1. Let's multiply that by the square root of, feel free, if you have x plus 2, feel free to rewrite that as x minus negative 2. If that really helps you say, my h value is not positive 2, it's a negative 2. I'm subtracting h. The only way to get this as x plus 2 is if h was negative 2. Now your k value is 0 because it's missing on the outside. So a couple things here. 1, your vertex is at the point negative 2, 0. And I don't know if they call it in a square root a vertex. It has the same function in a vertex as a quadratic equation does, the U shape, but it doesn't have two sides of it. It's a half parabola. So it's kind of just a starting point, but it's going to start right here. There's the vertex. And the stretch factor is 1. This a value is 1. And this is just by default. It's not going to affect anything any differently from the parent function of a square root thing. So the square root guy, now what I'm going to do just to make sure that it makes sense for this problem and maybe even the next problem, is I'm going to start at 0, 0 because I want to start by graphing y equals the square root of x so you understand exactly how to graph these. Okay, for y equals the square root of x, when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is the square root of 2. I don't really know how to plot that. X is 3, y is the square root of 3. X is 4, y is the square root of 4. Now that number's 2. I can plot that. 5, 6, 7, and 8 don't have a square root. They're not perfect squares. 9 does. You go over 9, you go up 3. So if you know some of these points, if you know 1, 1, 4, 2, 9, 3, 16, 4, 25, 5, 36, 6, what am I doing? I'm taking a square root of a perfect square. 49, 7, 64, 8. Now, you don't have to go that high necessarily. You really just need a couple points, maybe a few. But this is all that this graph is going to be. It's just going to be that and look like that. Now, this is the parent function so of y equals the square root of x. This one is the exact same thing, but it's shifted. So ideally, the only thing that this graph does is it's just right here. Now, I am going to regraph it, but this is what your graph's going to look like. The stretch factor is the exact same, okay? And I don't know if we're doing any other graphs without stretch factors here, so I will show you a different stretch factor for this problem right after we finish this one. And there's just a shift. Otherwise, it goes in the same direction and it hits those points. So everything that I do, that 1, 1, everything like that, that's just in relation to your vertex. So find your starting point and then graph from there. That'll be perfect. You'll be able to find everything just as you need to. So we have the point negative 2, 0. This is essentially at 0, 0. Like, you know, this is your default starting value. So with a stretch factor 1, I just go 1, 1, 4, 2, 9, 3. Now, this value is not 9, 3. This value is 7, 3, right? But it's 9 away from the vertex. That's what I'm talking about. Everything here is in relation to the vertex. And we can use a table to talk about why that is with the equation. But let's reserve that for a later time here. And there is your graph. Now, it doesn't actually flatten out. I'm just not good at drawing. There you go. There's y equals the square root of x plus 2. So get the information out, understand how stretch factor works, how you can graph without a table. You'll be all right. I'm going to go ahead and show you what it means to have a different stretch factor, though. Let's say, instead, this problem said y equals 3 root x plus 2. Heck, I'll do a new problem entirely, not just x plus 2. How about 3 root x plus 2 minus 4? Now your vertex, quote-unquote vertex, it's at negative 2, comma, negative 4. Remember, this is a plus k on the outside. To have negative 4 on the outside, that must mean your k is negative. So it's at negative 2, negative 4, and this is where we're going to start. Now, the a value of 3 changes what exactly? Well, it sits outside of your square root. The 4 is shifted afterward, but the 4 is just something to do with y that it doesn't change your scale so much. You're going to take this value and you're going to triple it. So what actually happens here is, remember when we went over 1 up 1? Let's do this again without that thing. I'll do this in purple as temporary ones. Over 1 up 1, over 4 up 2, over 9 up 3. Well, this time we're going to triple these y distances. Instead of going up 1, we're going to go up 3. Instead of going up 2, we're going to go up 6. Instead of going up 3, we're going to go up 9. That's what this a value does. It vertically stretches these points here. Over 1 up 1, 2, 3. Over 2 up, over 4 up 1, 2, 3, 4, 5, 6. Triple your distance away. Over 9 up 1, 2, 3, 4, 5, 6, 7, 8, 9. You're tripling the number 3. Now your graph looks a lot taller like that. There we go. So that's what 3 does, and if I made it negative, it would do the exact same thing, only it would go down 3, and down 6, and down 9. And if I made it 1/2, it would be half this distance, half of 1 right there, and half of 2, which is 1, and half of 3, which is 1.5. So it shrinks and grows your vertical length of it. Now it's all with respect to where your vertex is at. This is everything about distance from vertex, not about 0, 0. Essentially, you're at a new vertex here. That's all. What some people actually do is they only apply the stretch factor first, meaning they'll start here. Oh, excuse me, 3. We're using 3 though. Like this. 1, 2, 3, 4, and 9. They'll start here. And then what they'll do is they'll say, okay, I want to shift all these points this way. Left 2 and down 4. 1, 2, 1, 2, 3, 4. Boom. 1, 2, 1, 2, 3, 4. Boom. Like that. Okay. It's kind of a tricky way of doing it because you have to keep focus on the points that you were supposed to be on. And then they erase the other points. And then they go ahead and graph. So at least that way they say, what the heck do those things have to do with it? Well, they kind of take place at the end. So you can graph it that way as well. Okay, let's do the last one here. Now, this last one, I will talk about something that I haven't really talked about in any video yet. I take that back. I made made mention of it once, but I did not do it in a problem. I don't think. Y equals x squared minus 4x. All right. This is not in this quadratic form. So we have many options to do here. I'll try and tackle all of them without using a table, mind you, or a graphing calculator. One thing we could do to get us kind of started, especially, because we're trying to get really specific points, but one thing that could get us started for any of this is we could find out what the x-intercepts are. Okay, now we know what the y-intercept is. It's 0. X squared minus 4x plus 0. So your y-intercept is 0. This is a good start, 0, 0. But then you also then know that that's one of your x-intercepts as well. But we'll find that out in another way. We can factor out an x. Oh, and for x-intercepts, we're going to set y equal to 0. And over here, you can apply what's called zero product property, meaning if this quantity times this quantity equals 0, then either this equals 0, which is one that we already have plotted right here, or this equals 0, where x would therefore equal 4. So your two x-intercepts are the points 0, 0, and 4, 0. So one graph is there. Let's do it in blue. One point is there, and another point is there. A couple other things you can do. We can find the vertex of this with our x-intercepts. We know that all parabolas are symmetrical. Yeah? All parabolas are symmetrical, and by the kind of symmetry they have, they go upward or downward, straight up, so that these 2 points are corresponding points that are just on opposite sides of the axis of symmetry. What all of that means is if I could find the axis of symmetry, the guy that's right down the middle of those two things, what I have to do essentially is find the midpoint of the numbers 0 and 4, which is 2, 1, 2, 1, 2. This line right here of x equals 2 contains the vertex somewhere on here. Now, how do you find it? We got to find out what y equals when x equals 2. Right? If x equals 2, we can substitute our own values. We can substitute 2 for x and figure out what y will be as a result. Okay, so let's take this equation, the original one. Let's substitute 2 for x. Let's figure out what y becomes. 2 squared minus 4 times 2. So y is going to equal 4 minus 8, which is negative 4. So your vertex is at the point 2, comma, negative 4. 2 over 4 down right there. Boom. So this is the bottom of it. You can tell that it goes upward. From here, well, first of all, you might have enough for a quadratic whatever, but I can find more points. I'm going to apply the same idea that I applied with the square root one. The square root parent graph, I use the square root parent graph. The square root quadratic graph, x squared, I start at 0, 0, then I go over 1, up 1, over 2, up 4, over 3, up 9, over 4, up 16, 5, 25, 6, 36, etc. The other cool thing is it also reflects right on the left. Negative 1, 1, negative 2, 4, negative 3, 9, negative 4, 16, negative 5, 25, negative 6, 36. As long as you understand how to square numbers, you'll be okay. This is also true for cubing numbers. As long as you know how to cube numbers, you'll be just as fine. So what I'll do is I'll start from the vertex and I'll apply that same principle. Now our stretch factor here is 1. If there's one thing I can talk about with standard form here is that standard form looks like this and vertex form looks like this. Okay. Besides x and y, the only constant that's the same is a. And yes, this a means the same thing here as it does here. And we're going to make sure to do that as well. That'll be the last thing. Or, I have 2 more ways to do this problem. That'll be one of the last 2 that I do. So the a value is the same. So in this one right here, your a value is 1. And as we know in this thing, a represents stretch factor. So our stretch factor in this problem is 1, which means we apply it just the same as we do this. 1, 1, 2, 4, 3, 9, 4, 16, etc. So here we go. 1, 1, 2, 4. Look, we already have a point there. 3, 9, 5, 6, 7, 8, 9. And 4, 16 is probably a little too high. I probably can't plot that point. Now, you could do the same counting thing over here, but because of this axis of symmetry, I know that points correspond, meaning there's a point at this same height that is 1 unit away from the axis of symmetry on this side. It's right there. Now, I don't care what these points are. You know, like, I don't care that the point is 1, negative 3. I'm very, very not of concern of that point. I just care where it is in relation to this point or in relation to this point. Same with this one. I don't have to count 9 up. I can go 1, 2, 3 away from here. 1, 2, 3 away. At the same height, there will be another point that's like that. So your graph, now this will not be a good looking curve. I shouldn't speak too soon. Yes, I will. Your graph will look like that. So the first way that I went about this kind of problem was I found my intercepts, because this was standard form, right? I found my intercepts. My y-intercept was 0, 0. My x-intercepts were 0, 0, and 4, 0. I found my vertex by having it be right down the middle. And then I had to find at least one more set of points so I could reflect. What was actually unfortunate with this problem is that the y-intercept and one of the x-intercepts were actually the same value. It's actually really nice when they're different values, because then you can find 4 points off the bat by doing y-intercept, 2 x-intercepts, the vertex, and then there will be a corresponding point that's mirrored the y value, kind of like these 2 were. So you can find 5 points immediately. And to me, 5 is really the satisfiable number for quadratic things. But also for me, as many points as I can plot, I will plot them for you. Okay, so that's one way of doing that problem there. The y-intercept, x-intercepts, vertex, and any other points that you can mirror or find using the stretch factor. Second way of doing this problem is by completing the square. Do this in green. Completing the square. Now, in completing the square in this case, why would I do it? Because maybe I'm trying to find my vertex, HK, and I can only do it if it's in vertex form. And it's not in vertex form unless I can get a perfect square trinomial factored into this factored form right here. And I can't do that unless I complete the square. So here, I have y equals x squared minus 4x. Nothing else is there. So what I want to do is I want to find a number to add right here. Whatever number there that'll complete my square. Now I can't do this unless I keep my equation balanced somehow, which either means add the same thing to this side, or better yet, just subtract the same thing from this side. Whatever I add, I'm also going to subtract again. Now you're like, what the heck? Why are you doing that? You're just going to waste time. Well, I'm not going to combine these two like terms. I'm going to use this term very specifically inside this trinomial because it'll be factored into a perfect square trinomial. This will be hanging on the outside. So what number goes here? Well, if you want to learn more about completing the square, make sure you check out the solving equations algebraically and graphically video. But I'm going to take this number here, this -4. I'm going to divide it by 2. That number is -2. And I'm going to square that number, square it, and that number is +4. This is the number that's going to be here. This gives me a perfect square trinomial. Again, please watch the other video if there are any questions on that. I hope I do cover it enough in that video. So I added 4 here. Now I've upset my balance in my equation, so I must also subtract it outside here. But what's beautiful now is I have a perfect square trinomial that I may factor. I may write into factored form. And it's going to factor into -2. You know, x minus 2 times x minus 2 looks like that. And on the outside sits a -4. There we go. Now I'm in vertex form. Excuse me. The one thing that you don't see out here is the A, and the A value is 1. So there we go. So your vertex is at the point 2, negative 4. You have an A value of 1. So you've only found 1 point so far, but if you know how to use the stretch factor from it, this is perfect. The other one, you might have had trouble doing it if you didn't know where your vertex was. Even if you knew how to do stretch factor, you might have said, yeah, but I don't know how far away these points are from the vertex. I don't really know what to do here. I only know how to do it starting from the vertex, and I understand that. So if you didn't know how to find it this way, you can find it by completing the square as well. So getting that vertex point, then using that A value of 1, going 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, reflect across, or negative 1, 1, negative 2, 4, negative 3, 9, etc. Okay? So it's option number 2. Option number 3 is kind of the same as option number 2 because we are trying to find the vertex first. But option number 3 is in finding the vertex when it's written in standard form. Y equals x squared minus 4x. Okay. Third option is you can find the vertex using the following. For x, it's going to be at the value negative b over 2a. The y value is going to be what you get when you plug in negative b over 2a in for x, and you solve for y. This looks very strange. When I mentioned this, because that's when I realized I did talk about this, when I mentioned it in a video, I was talking about quadratic formula. And I was saying that in the quadratic formula, you have this whole thing right here, okay? If I split up this denominator, it's going to be negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. Now, I might not have made a lot of mention about this part right here. I know I said that this is how far away your two intercepts are from your vertex in the x direction. So, for instance, this number, when I jump this much, I've jumped positive square root of b squared minus 4ac over 2a. When I jump this much, I've jumped negative square root of b squared minus 4ac over 2a, because that's how far away they are from the vertex. But what's better to talk about is if b squared minus 4ac was 0, then you'd be looking at a problem where your x-intercept and your vertex are the same thing, which would mean this is your x value for your vertex. So negative b over 2a is that exact value. So we calculate what negative b over 2a is by this being in standard form. A is 1, b is negative 4. And we're going to find the x value of the vertex by doing negative b over 2a, which is 4 over 2, which is 2. To find the y value, you go ahead and you substitute 2 in for x into here. Now, we already did that way up here. You substitute in 2, you get negative 4. So you get your vertex of 2, negative 4. So you go back to there, you use your stretch factor of 1 that you had right there, and you mosey along. Now, vertical stretch factor, if a was like 2 instead of going over 1 up 1, I'd go over 1 up 2. I'd double the number 1. Instead of going over 2 up 4, I'd go over 2 up 8. Instead of going over 3 up 9, I'd go over 3 up 18. So I just double my previous number if my stretch factor was different. But start from that vertex, figure that out, or use that first method that I talked about here in standard form. But if it's already in vertex form, which is what you've mostly seen, you're kind of good to go. You just got to know how to apply the stretch factor after you plot your vertex. Cubics are the same. All these other ones are the same, but these are the only problems we're running into like this. Okay, we're going to determine algebraically any points of intersection of the graphs of the equations. We're going to use a graphing calculator to verify our answers. So right here we have two equations. They say algebraically. So to do it algebraically, we can find it by using the substitution method or the elimination method. This one's already pretty set up for the elimination method. It would take a while to do substitution method because there would be fractions involved. I'm going to skip that one, so I'm just going to go ahead and do elimination method. Now, elimination method is about lining up your x's and y's and constants and adding down the list. And we can add down the list because we're adding the same thing to both sides. To 3x plus 5y, I'm adding this value. To negative 7, I'm adding this value. These two values are equal. So technically, we're adding the same thing to both sides, but we're giving them the ones that can combine like that. So this would be 2x plus 3y equals negative 4. Now the problem with me adding down like this is I didn't eliminate anything, right? So what we want to do is we want to be able to eliminate something with this. So this doesn't help us do that. So what we have to do first is manipulate at least one of these two equations so that we have additive inverses on the top and bottom. What I would say is pick a variable you want to eliminate. And it's not just pick one out of the blue, flip a coin. It's look at both of them and say, which one do you think is easier to do it with? Okay. I think it's going to be easier if I multiply the bottom equation by some number instead of the top. And I can't multiply negative 2 by an integer to get negative 5, but I can multiply negative x by an integer to get negative 3. So I'd say we multiply the bottom by 3 so then we can eliminate our x's. So I'm going to rewrite the top equation here. I'm going to rewrite the bottom equation, but with 3 multiplied with every term. Keeps my equation balanced. Negative 3x minus 6y equals positive 9. Okay. Now when I add down, 3x minus 3x is 0. 5y minus 6y is negative 1y. And negative 7 plus 9 is positive 2. So if the opposite of y is 2, then y is negative 2. So I found the y value. Awesome. The x value, now you just kind of substitute. You take your negative 2 value, substitute it into one of these two equations, or even this manipulated one right here, and you find x. I'll do it with the top one right now. 3x plus 5 times negative 2 equals negative 7. 3x minus 10 equals negative 7. Add 10, 3x equals 3. Therefore, x equals 1. So your final solution there is 1, negative 2. Write it as an ordered pair, please, because this really is about the point of intersection, not just solve for x and y, which means that whenever these two, because these two things are graphs, right? They're written in standard form right now. We could graph them using the intercepts that way. I could put them into slope-intercept form, but I'm going to do it with the graphing calculator, right? Use a graphing utility, because I think I get fraction y-intercepts, and you know how much I don't like those. So 1, negative 2, boom, boom, boom. Wherever these two graphs are, let's say it looks like this and this, they're intersecting at that point. That's what it means. This is a solution to both of the equations. This is the only one that's a solution to both of them, both at the same time. Okay, so let's determine this graphically here. I'm going to go ahead and turn this thing on. Now, what I do have to do this time, though, is I must actually put these equations into slope-intercept form to make this happen. So although I will be dealing with fractions, although I will have solved for fractions, I don't have to really deal with them in that I have to use them to calculate stuff. I just got to punch them into y equals. So this top equation, let's do 5y equals negative 3x minus 7. Divide by 5, you get y equals negative 3/5 x minus 7/5. This will be one of the equations I put in the graphing calculator. The other equation I'm going to put in the graphing calculator is by solving for y in this one. It'll say, adding x as negative 2y equals positive x plus 3. Divide by negative 2, it'll say y equals negative 1/2 x minus 3/2. So obviously the graphs don't look like the ones I just graphed, at least not this one, because both slopes look to be negative. But let's go ahead and graph them and see how they look. So the first one is negative 3/5 x minus 7. The second one is negative 1/2 x minus 3/2, minus 1.5, right? Minus 3/2. Okay. We don't have to do it this way. We could do it just in our table, but we use the graphing utility for it. But let's just take a look and see that this thing works this way as well. You may do it any way you'd like, and I'll show you every way possible. So I use the graphing utility. I watch these things go through. Did I do something wrong here? Negative 1/2 x, negative 3/5 x. Oh, minus 7. This should say minus 7/5. I'm sorry. Here we go. Try it again. Here's one of them. There's one of them. And you can see they do intersect somewhere. And you can imagine, oh, they might intersect right here. Yeah, they just might. Let's go and zoom in. Now, even if you don't want to zoom in and do all that, we can use the intersect function. And that's what I'm going to do next. But you can see it a little more closely here. Okay. Looks like they do intersect at about that spot. Let's confirm it by doing Second button, calc. Let's find the intersection of these 2 points. First curve and second curve, what they're asking you is which curve would you like to select as your first and your second one. So you can see as I go to the more to the left, it's the one that's on top right there. The second curve in comparison, we're going to do this one on the bottom. So we're going to intersect these 2 curves, and guess just says get close to your location, because if there's more than one location they intersect, we're going to find that one for you if you're close to it. But there's only one for linear equations, right? At least in this case. And it intersects at the point they tell you, 1, -2. And there it is. Whoop, there it is. Hope I don't have to pay anything to make that statement. Okay, the other way I could do it is going to my table here. And what I'm going to do here basically is, here are your x values. And for the y values, this is for the equation in blue over here, y1. And y2 is for the equation in red right here. And you're just looking to see which value gives you the same thing on both things. And obviously it's at x equals 1, because this is when y is -2 for both. You can see no matter where else you go, you won't have that. I wouldn't always recommend you do this, though, because what if it doesn't land on an x value that is an integer, right? That's why the intersection one's just as good. But this one also confirms, really, it's the only place it's going to happen. And I think we understand that as much with equations. And that's how we can verify our answer there. Or furthermore, what we could do is we could say we solved, because it said to verify it, right? Not to solve this way. So we already solved it. And what we could do through verifying it is we could just ask the calculator a value for x, like 1, and then we say, okay, what y value do we get? If we get the same one, it's awesome. If we solved it and we got x was 15, and we tried 15 for x here, you can tell it's not the same answer. So you know that your 15 answer is wrong, or you typed something wrong, because as you saw, I forgot to type 7/5 before. Okay, but that's how we use the graphing calculator to double check that. Let's solve the inequalities here in x. We have an absolute value problem. We have a quadratic problem here. We're going to solve the inequality and graph the solution on the real number line. Use a graphing utility to verify your solution. Okay, fair enough. For an absolute value problem, it is crucial that you isolate your absolute value before you do anything else, in which case there's a 4 being multiplied on the outside of this absolute value. Let's divide both sides by 4. Now we have the absolute value of 3 minus 2x is less than or equal to 4. Now that we have the absolute value of this, it's within 4. So the number, not x, but the number inside it here. This number, I take the absolute value of this number, and I get a number that is 4 or smaller, meaning it's between the numbers 0 and 4, right? So that means the only range I can pick in between was a number on the number line. It would have had to be between the numbers -4 and +4. Because let's say I took the absolute value of -10, okay, well, that number's 10. That's sure not less than 4. So you know that has to be between -4 and +4 for this to work. And the way that we write that is either 3 minus 2x has to be less than or equal to 4. Or when we do 3 minus 2x, it has to be greater than or equal to -4. Okay, so it has to be within those two. Some people write it as a compound inequality on the spot, where -4 is on the left, 3 minus 2x is in the middle, and 4 is on the right here. And you know what? We can practice it this way. And really, this wasn't an or problem. It's an and problem because it has to stay within. So yeah, sure, let's try it this way, because then we can practice some things here. Okay, we got to get x by itself. Now, here's the middle term, or here's the middle spot with x. We're going to try and get it by itself there. Whatever we do here, we're also going to do here and here. So to start getting x by itself, I'm going to subtract 3. Everywhere. -4 minus 3 is -7. There's a -2x inside here, and there's a 1 inside here. Now to solve for x, I have to divide by -2. Now, one thing about dividing by negative numbers with absolute values, with inequalities, is that the inequalities flip. So if I literally just flip them right now, I'd have -7 over -2 is positive 3.5. This inequality would flip and look like this. Now these cancel, and you're left with x, and this flips this way, and 1/2 is positive 0.5. Negative 1/2 is negative 0.5. So now it looks like this as a compound inequality. Well, the one thing, when it comes to syntax, if you looked at an answer in the back of a book, if you talked to whatever, you don't want them written this way. You want your arrows to be facing to the right, not to the left here, okay? So ideally, I'm just going to take my 3.5 and I'm going to bring it on this side, and then negative 0.5, bring it on that side. Just make sure that you kind of get your alligator mouths, your greater than, less than, your inequality symbols. Make sure you get those flipped as well. Because as x is greater than or equal to negative 0.5, negative 0.5 is also less than or equal to x. And as 3.5 is greater than or equal to x, x is less than or equal to 3.5. So this is a proper way to write that compound inequality. Maybe it's safer that you start this way. You solve for these two separately, and then you put it in a compound inequality. And some people don't put it in a compound inequality. But if you don't, you might make the mistake of remembering that they have to stay in between each other. And furthermore, you really do have to use that word and if they are supposed to be in between each other. If you leave it blank, that's not too bad. If you use the word or, it's going to be an issue because it's not or. It needs to satisfy both solutions satisfy both inequalities at the same time. So subtracting, dividing, you'd get this, negative 1/2, negative 0.5, I'll just put that. You get this, and subtracting 3, you get negative 7, dividing by negative 2, you get less than or equal to positive 3.5. So you can also write it like that and then convert it into that compound inequality, but make sure that when you graph this on the number line that you keep in mind it needs to stay in between these two values. So let's go ahead and graph it now using one or the other. Now the thing with the compound inequality also is that it's helpful to have the smallest number on the left because now you're reading it just like this. X is in between this number and this number. Just like when I do it here, there's 0, there's negative 0.5, here's 3.5. We know that x is in between these two numbers, and it includes them, but x sits between this one and this one. So it's kind of good to have it in the proper left to right order anyway, never mind the fact that it should be written in that order. There we go. Nice little line. There's x. There's your graph. It sits right in between. So any number that I substitute within this solution set, including 0, will satisfy the original inequality. What was the original one? Way up here. If I substitute 0 here, I'm going to get 3 minus 0, that's 3. The absolute value of 3 is 3. 4 times 3 is 12. 12 is less than or equal to 16. It's less than it. And that one works. And so does anything else that I would put into there. That would definitely satisfy it. Okay. I think this is the last one here. Last one is a quadratic, and I'm not going to reintroduce the entire concept, but I will say that it's recommended that you put this thing on this side of the inequality for a few reasons. One, if you know or remember anything about this, we are going to be testing values for x against the inequality. So if we test values for x, it's easier to test something against this threshold because all we're testing is it positive or is it negative, as opposed to is it greater than 3 or is it less than 3, right? Positive versus negative is a lot easier to just do. 2, when we solve for this thing anyway, it's easier to solve for things right here in quadratic form, like in standard form of a quadratic equation, because if something's factorable or if you're using quadratic formula, this is probably the way to go about it. If you want to do completing the square, this is fine. But solving it this way is good because 3, when you solve it like this, you know that you're finding the x-intercepts because what you're doing is you are comparing this equation, which is a parabola. In other words, by this equation, I mean y equals to this equation right here. And y equals 0 is the x-axis. And when these two graphs are equal is when you're finding the x-intercept, is when they're intersecting on the x-axis, meaning it's the x-intercepts. So it's really nice to just talk about it in that fashion because then you know where the intersection point is and you know that you're comparing above and below the x-axis is all. So when we do use a graphing utility to verify the solution, which by the way, I did not do that on this one yet. I believe I can if you'd like me to. But when we do it for this quadratic one right here, we must find some critical points, and it's a lot easier to test against the inequality to the left and right of the critical points if we have 0 on this side. Just a recommendation. So first thing we have to do is we have to find critical points. Critical points are the points of intersection of these two graphs right here. So when these two are the same y value. What are the x values that give you the same y value? Well, in factored form, and by the way, I'll do all three for you. I'll do factored form, completing the square, and quadratic formula. Now, I'm not going to do a lot about factored form. What two numbers multiply to -3 and add to -2? Well, -3 and 1. So if those two multiply to equal 0, zero product property would state that if one of these would have to be 0, either that or that. In this case, x would equal 3, or x could also equal -1. These two are critical points, which means if I substitute 3 or -1 into the original inequality, like even this original inequality, but this one as well, then the left side and the right side would be equal. And by the way, those exist as a part of our solution set because it's greater than or equal to. So those are the critical points. We know that if I substitute -3 or 1 right here, not -3, 3 or -1 right here, I'm going to get 3 on this side and 3 on that side. I need to compare numbers that will be different. So I need to compare to the left and right of the number -1 and to the left and right of the number 3 and figure out whether things will be less than or greater than 3, or in this case, less than or greater than 0, whether they'll be positive or negative. Because the thing about these two graphs is, here's a set of axes, here's a parabola, here's this thing right here, maybe these are the points. I got to figure out what things will be above and what things will be below. I want to find the ones that are above because mine's greater than or equal to, and those will be a part of the solution set. So let's go ahead and, well, actually, before I do that, I have to solve by completing the square by quadratic formula. So I'll do two more ways. Let's go way down here. X squared, yeah, there's a lot of room. X squared minus 2x minus 3 equals 0. If I want to complete the square, once again, it's probably just good that I bring that 3 over because the -3, because it doesn't have anything to do with my perfect square trinomial. It's just getting in the way. Now, in this case, I'm just going to add the same number on both sides. So -2, I'm going to take this number -2, I'm going to divide it by 2, that number's -1, and I'm going to square the number -1, that number's 1. Then I'm going to add 1 on this side as well to keep it balanced. X squared minus 2x plus 1 is x minus 1 quantity squared, and that equals here 4. Taking the square root of both sides, sorry, the square root of x minus 1 squared is x minus 1. The square root of 4 is 2, but you have to consider both cases positive or -2. Because if I substitute -2 into here, -2 quantity squared is also 4, just like +2 quantity squared is also 4. There are two solutions to consider. Add 1 to both sides, you'll get x equals 1 plus or minus 2. And you don't leave it like that, just evaluate them. X is either 1 plus 2, or x is 1 minus 2. 1 plus 2 is 3, 1 minus 2 is -1. Same solutions as we had before, same critical values. Third way is through quadratic formula, and of course quadratic formula is proved by completing the square. That's how you can prove quadratic formula. X equals, it's all up here, -b plus or minus the square root of b squared minus 4ac all over 2a. We can do that as long as we are written in standard form like so, where a is 1, b is -2, and c is -3. If that c was on that other side of the equation, then that's not the value of c. But this one is right here. I like to start with the discriminant, b squared minus 4ac, because it's just easier to compute things right now, outside of writing everything else. And then we'll go ahead and put this in our quadratic formula when we're good and ready. This is 4 plus 12, which is 16. So our discriminant, the guy inside the square root, will be 16. So when we do quadratic formula, it'll say x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So let's continue going. X equals 2 plus or minus 4 all over 2. So either x equals 2 plus 4 over 2, or x equals 2 minus 4 over 2. So 6 over 2, 6 over 2 is 3. 6 over 2, or -2 over 2. There you have it. So 3 different ways to solve for that thing. If it's not factorable, you got to really use completing the square or quadratic formula to solve for it, but it was factorable. I could have started from there and just moved on. So these are the 2 critical points. Once again, to the left and right of these values differentiates the left side from the right side. We got to figure out which ones makes the left side, which values of x makes the left side greater than the right side. Or on a graph, that means which makes the y values on this set of points taller, higher up than y equals 0, than the x-axis, the ones that are in the positive direction, on the positive end of y. So what are our points? 3 and negative 1? 3 and negative 1 are critical numbers right here. So we are going to test to the left and right of these values. So what I'm going to do is kind of make a table of x and y. We know that negative 1 and 3 are kind of involved right here. I need a number that's less than negative 1. How about negative 2? I need a number that's between negative 1 and 3. How about 0? I need a number between greater than 3. How about 5? Because remember, anything that I plug in, it could have been 5, it could have been 1,000. It would still give me a true or false statement for the inequality. Now, what was my inequality? It was x squared minus 2x minus 3 is greater than or equal to 0. So I have to find out which ones will make this statement true. Let's try negative 2. Negative 2 squared is 4. Minus 2 times negative 2 is another 4. So 4 plus 4 is 8. Minus 3 is 5. 5 is greater than 0. This is true. Remember, negative 1 will give you 0. So that's also true. Not that you have to test it. Same with 3. I'm just kind of letting you know. 0 squared is 0, minus 0 right here. Minus 3 is negative 3. Negative 3 is not greater than 0. That's false. It's not equal to it either. 5 squared is 25. Minus 2 times 5, which is 10, so 15. Minus 3 is 12. 12 is greater than 0. This is also true. Now, you don't really need these 2 zeros right here. Really, all I needed were these parts right here because we need to figure out which ways x can go. So, again, on that makeshift graph that I drew before, I knew it was a positive parabola. I knew it was crossing at negative 1 and positive 3. And we're going to verify this on the graphing calculator. It's going to look just like this here. But if I choose 3 or negative 1, I'll get 0. Those are fine. If I choose a value like negative 2, I'm getting a point up here. If I choose a value like 5, I'm getting a point up here. If I choose any value like 0, I'm getting points down there. These are not greater than 0. These are not equal to 0. These are no good. These are. So what's my solution set? Well, x can be less than or equal to negative 1, because like negative 2 and anything else, or, and or is the big word here, x can be greater than or equal to 3, like 5 and such. If x was 0 or 1 or 2, those are no good. So how do we graph this? Well, we graph it on a number line. Okay, we're not going to graph like this kind of graph. It's not one of those sketching things. We're just doing it like so. Number line of 0. I like to put 0 in there. Negative 1 and 3. It includes negative 1 and 3. So close circle, and they're going this direction and this direction. All right, so I promised I'd graph these. Let's do the absolute value one first. And really, I do want to compare the original graphs, so you don't think that I'm just doing the isolated ones. I want you to see what the original ones were going to look like. So I'm going to set y equal to this and y equal to this. Then later I'm going to set y equal to this and y equal to this. And we'll see exactly what we're looking at in these graphs here. So graphing calculator, let's go and do these y equals. Clear these ones out though. Okay, y equals 4 times the absolute value. Here I go to the math button here, and abs is right there in number. 4 times the absolute value of 3 minus 2x, okay, versus 16. Okay, now when we're graphing this, and remember, in this case I kind of need a bigger window because I need to get up to 16 there, so I'll scale whatever. Let's go from negative. Oh, x's, I need bigger ones. Actually, I don't. Remember, I'm just checking from this range. So how about let's go from negative 5 to 5. This will be a stretched graph, a vertically stretched graph here. And I'm going to go from, I don't care about my minimum, I don't think. My y max I need to get a little tall, though. Let's go up to 20. Let's see what this graph looks like. So there will be two lines here. There's going to be the absolute value line, boom, boom, and that one right there. Boom, boom. And what we're looking at is, here's where they intersect. Now, we could have done this critical number stuff with the absolute value stuff, but it's not as important because we know how to separate both these equations immediately. This will matter a lot more for the next one I do. But here's where they intersect. Around here, around -1/2, and then around +3.5. What we wanted to check and see is what values of x do we substitute on the left side so that they become less than 16. In other words, where the absolute value graph is underneath the horizontal line. So here's the absolute value graph from -1/2. Sorry, this is a slow scroller. From -1/2 to +3/2. Notice how all these points are underneath the horizontal line. That's what we wanted. They had to be less than it or equal to it. But if I substituted another value, like, I talked about a number like I forget what number I said, but if I put like -5 or something like that, well, it would be above that line. So it's no good. That does not satisfy it. So like I said, you can do the critical numbers thing here. Just we have another technique here, and it's fine. Over here, we have to do a little bit more to solve for it. Okay, so that's the absolute value one. Now the quadratic one, I'll do the original equations, and then I'll show you what the difference is between this set of equations and this set of equations. Then I'll nip it in the bud, and we'll move on to the what I actually think are the last two problems, because it's more of the testing these things. So at least I don't have to explain it as much then. Okay, so these two graphs here. Let's look at the graph. Parabola, y equals 3. Okay, so this is where they're intersecting. -1, 3, and 3, 3. Now, how come they're intersecting at the same point as the other ones? Well, because these graphs are nothing more than the exact same graphs as the last ones, but they're shifted up 3 units. So if I graphed the other two right next to it, so if I did x squared minus 2x minus 3, it was minus 2x minus 3, and I did 0, which is the x-axis, and I made these ones a little darker so you can see exactly what's going to happen. I want you to see how they are the exact same thing but only shifted down further. So redraw them, those two, and then these two. Boom. You might say that's fatter. No, it's not. It's just shifted down. So here at -1, it's at 0, and 3, 0 as well. So just shifted downward, it's the same thing. So that's why I just tested against 0 as opposed to against 3. But the test, remember, even if I did the original inequality, the test is just to say when I substitute values, when I substitute values for x, what values of y will be above 3 and what values of y will be below 3. I want to know which ones are above specifically, right? So if I plug in 1, it'll be at 3. Actually, that's okay. If I plug in these will also be above 3 right here, that are less than 1, and ones that are greater than 3. Okay? On this side, below it, or not on this side, but below it here, they'll be less than 3. Not about being negative. Even these ones are less than 3. This one right here. So that's really what we're testing, and I won't be focused on that too much anymore now that we're going to move on. Okay, last set of problems here. Whoops. So same thing, solve the inequality and graph, use the graphing utility. Okay, this one's a cubic function, but what we can do and what you really should do each time to solve for this thing is you really just want to find a common factor if you can. In this case, x can be divided out, and left hand side is x squared minus 16. Now you have a quadratic inside there, and you can keep going and factoring that. This actually becomes x plus 4 times x minus 4. It's greater than or equal to 0. Now you don't have to do this stuff from the onset. In fact, I should be setting it equal to 0 right now, because the first thing I have to do is find the x-intercepts, because these will be my critical numbers. Now I like that it's already set equal to 0, right? So if this times this equals 0, either x equals 0, or x plus 4 equals 0, or x minus 4 equals 0. X plus 4 equals 0, x equals -4. X minus 4 equals 0, x equals +4. So these are your 3 x-intercepts. These are your 3 critical points. All of these points I'm going to test to the left and right of, just like last time. So I can speed up this problem instead of re-explaining everything, but I will look at the graphing calculator and figure out how they compare afterward. So the numbers are -4, 0, and 4. Unfortunately, this time 0 is not a number I can test. Left of -4, let's go bold. Let's try -10. Between -4 and -0, and -1. 0 and 4, 2. How about 6 over here? Okay. Now I'm testing it against this original inequality. X cubed minus 16x is greater than or equal to 0. So I have to see which numbers will yield positive results. All right? -10 cubed is -1000. -16 times -10 is positive 160. -1000 plus 160, even if you didn't know what the answer was, you know that it's negative. If it helps, the answer is -840. That is false. That is definitely not a positive number. Sorry. -1. -1 cubed is -1. -16 times -1 is positive 16. -1 plus 16 is not only a positive number, it is positive 15. That is greater than 0. That is true. 2. 2 cubed is 8. Minus 16 times 2, so 8 minus 32, negative number. False. Sorry, I was going to write a T. Finally, 6 cubed is, oh boy, 216. Minus 16 times 6, why did I choose such a big number? Minus 16 times 6 is 5, 6. Boy, I'm slow today. 96? 96? 96? Yeah, 96. What was the first number? 216 minus 96 is 120. I might have calculated it wrong, but I know it's positive. That's true. So false, true, false, true. So when it comes to things being parts of the graph being above the x-axis and below the x-axis, you can see it right here. So what is the statement here? Well, x can be between and including -4 and 0. Or x can be greater than or equal to 4. Remember, we're using the critical numbers to determine all that. That's your solution set. There was a compound inequality and an additional inequality there. So number line, here we go. We got 0, -4, +4. Let's get x can be between these two. Right there. X can also be greater than them over here. If it is to the left of this or in between these, you get negative numbers. No good. Let's check that out in the graphing calculator so you see what this looks like. Or I could tell you what I think it's going to look like beforehand, and then we could confirm it. How about that? Not to show off, to show you the thought process, what's exactly happening. So what happens is you have a set of axes here. You have 3 different x-intercepts. They're at -4, 0, and 4. So they look like there, there, and there. We know that values to the left of -4 are negative values for your graph. So they're going to be below the x-axis. In a cubic function can have this behavior or this behavior. We know it's going to be the one on the left here, if not just for that reason, other than the x cubed is positive. So it's going to go up and through -4. Then it's going to curve and come back down through, whoops, it's going to curve and go back down through 0 here. And then it's going to go right back up again through 4 and do that. What are these exact points? I couldn't tell you. I'd have to use some sort of calculus for it. But this is the nature of the curve. And what we're seeing is between the numbers -4 and 0, you will be 0 or positive. Basically, you won't be negative. And greater than 4, you also won't be negative. But to the left of -4, you will. And in between 0 and +4, you will. And those are ones that we don't want. So let's go ahead and graph x cubed minus 16x here. Let's clear out everything else. Get out of my way, get out of my way. All gone. Okay, x cubed minus 16x. And we get good window range, I think. Let's see. Oh, no, too tall. Let's go -62 to +62. There we go. Hey, look at that. That matches up pretty good, actually. So There's the graph. There's the reasoning. Yada, yada behind it. There's my verification. It's good. Okay, last one. And I'm not going to graph this last one by hand. I don't like graphing rational functions. I know how to. It's not my forte. Okay. The only difference between these and these, besides the fact that I don't want to graph it by hand, is that there is at least one more, critical point, critical value that I want to find before solving this. And that is because your domain, in this case, is not all real numbers. There are restrictions because you got to make sure you can't divide by 0. So my denominator cannot be 0. So I'm going to set up something that says 3 minus x cannot be 0. If I subtract 3 over, negative x could not be negative 3, therefore x could not be positive 3. The number in the denominator that would give me 0, which would be an issue, is 3. Now, that is a critical number because what happens is it forms what's called an asymptote, and it actually changes the complete direction of your curve. Inverse functions look like this kind of thing with an asymptote there. To the left of a value will be like really negative, and to the right would be like really positive, something like that. So it changes sign there. Right? It doesn't just change sign where it passes through the x-axis, because sometimes it doesn't pass through. Sometimes it just makes up its own thing. It goes on the other side. So that's one of my critical numbers. To find any of the other ones, we have to solve for this. X minus 5 over 3 minus x equals 0. Multiply both sides by 3 minus x. This is actually kind of nice. What happens is they just go away. This one goes away, and 0 times 3 minus x is 0. So x minus 5 equals 0, so x equals 5. So not a very difficult problem when all said and done. So that's one of my other zeros, 5 and 3, apparently. So these are my two critical numbers. These are the ones I'm going to test to the left and right of. Let's go ahead and do that. Here we go. 3, 5. Left of 3, of course, I'm going to choose number 0. Obviously, it's between 3 and 5. I should choose 4. Let's stick close. Let's say 6. Okay. We have to test them to be less than 0. If they are greater than 0 or if they're equal to 0, which only the 5 will be equal to 0, then it will be false. So we got to make sure they're negative. Let's test 0. 0 minus 5 is negative 5. 3 minus 0 is 3. Negative 5 divided by 3 is a negative number. So that negative 5/3, that one is less than 0, so that one's true. 4 minus 5 is negative 1. 3 minus 4 is negative 1. Negative 1 over negative 1 is positive 1. That is a positive number. That is false. Finally, 6 minus 5 is 1. 3 minus 6 is negative 3. 1 over negative 3 is negative 1/3. That's a negative number. That is true. So your final solution set for x, it can be less than 3, anything less than 3. I chose 0 as my test one. It could be 2 or 1 as well. Or it can be greater than 5. So to graph that, I'm just going to erase this one last bit. Not graphing calculator. On a number line, I'll do the graphing calculator next. To graph that, it's going to look like, where's my 0? Right there. And 3 and 5. We'll go open circles on 3 and 5. We'll go to its left and right. Obviously, 0 is a part of the solution set. We tested that, and it worked. And there you go. So if we looked at this as a graph, again, we are comparing it to 0, so we just got to do y equals that part in the graph there. Let's see that. Y equals, love that curve. X minus 5, I got to put this in parentheses. X minus 5 divided by 3 minus, in parentheses, 3 minus x. It's just hard to do on the computer. I wish I could just actually push the buttons. So 3 minus x, close. Okay. Okay, you're going to see it go here and curve down and then curve and do that, right? That issue, the asymptote thing I talked about. So over here, as long as I am left of the number, what was it, 3? As long as I'm left, because 3 is my asymptote, it'll never hit 3 at all. We'll just converge at it. As long as I'm to the left of 3, my points will be any of these negative ones. Now, as they start to come up, they never get above 0 again. They actually just never do. It stays negative. It converges somewhere else. There's another asymptote here, something which we could talk about when we start graphing inverse functions. Now, to the right of 3, just a little bit to the right of 3, like 3.2, well, it might be a point up here, and 3.4, and 3.6, you know, whatever. All these points are still positive, all right? When do they start to turn negative? Well, once you hit the number 5, it's 0. Once you hit 5.2 or something, it's, you know, it's down here. It's a -2. I mean, I could use these. I could check these in my table. I could go to auto. Let's start at around 2.5. Let's go up 0.1 points each time here and take a look at the values, my y equals. They're negative, 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 get extremely negative. At 3 is an asymptote error dividing by 0. Then here they're positive again. Positive up until what point? Well, up until 5, 0. Positive, positive, 5, 0. Once you hit past 5, they're negative again. So that's what satisfies this inequality right here. That's the solution set. Okay, so that was a lot of talk, a lot of conversation there, but that is it. There will be another video that you'll be seeing around here that has some more example problems, but without the notes up top. So make sure you observe the notes up top, you see what it is you got to do with them, and you have some fun. You know, you get the stuff understood.